Hello everybody. Today we're going to start section 17.2 that deals with line integrals. So before we actually do the nuts and bolts on how to do a line integral, let's talk about the concept of what's going on here. Suppose I have a function f of xy, and I want to integrate the function f of xy over some curve c, which is given parametrically. And we could do this in 2 dimensions and 3 dimensions. For starters, we're going to do 2D, and then of course we'll not kick it up a notch and go to 3D. But c is given by x equals x of t, y equals y of t, and t is ranging from a to b. Now the whole idea of a line integral is that here's my curve that's going from t equals a to t equals b. And what we do is we break the curve into little subcurves. And in each little subcurve, we take a point in the subcurve, and we evaluate f at that subpoint. And then we multiply it times the length of that arc for each little subcurve. And what we're going to do is add all of those up. And as we let the number of subintervals go to infinity, this summation is called our integral of f of xy ds over curve c. So that's what the whole idea is. It's just an extrapolation from what you did in Calc 1 and in Calc 2 in terms of a simple integral. So the whole idea is you break up your break it up into little subintervals. Pick some point on the subinterval for each subinterval. Take some point, evaluate the function at that point, f of xy, multiply it times your arc length, and then add them up. Now the question is, how can we use calculus instead of having to do this limit? How can we use calculus? So I want to review just a little bit. You might recall, in fact, we did this in this course, and you also did it if you were with me in Calc 2, that to figure out the arc length of a curve, if we had some curve from t equals a to t equals b, and we wanted to find out our arc length, we had to figure out a parametric representation for the curve, x equals x of t, y equals y of t, t's ranging from a to b. And our arc length from t equals a to t equals b was figured out by taking the square root of dx dt squared plus dy dt squared times dt. Okay, you all with me? We could write this arc length as the integral of ds, as t is going from a to b. So this piece right here, we can think of that as being ds, square root of dx dt squared plus dy dt squared dt. If you have a curve that's given parametrically x equals x of t, y equals y of t. So what we're going to do in this particular section, and it's very easy, if we have to figure out the integral of f of xy ds, first sometimes they give you the parametric representation, other times you have to figure it out. But what we do is we get our parametric representation for c by x equals some function in terms of t, y equals some function in terms of t. And where we have f of xy, we replace x with that representation in terms of t. We replace y with that representation in terms of t. And we replace ds with square root of dx dt squared plus dy dt squared times dt. And then we do our integration from t equals a to t equals b, where t is what t needs to range from to go along that curve. And that's all there is to it. That's all there is to it. So let's do one. In this one right here, we're asked to figure out the integral along the curve 2 plus x squared y ds, where c is the lower half of the circle, x squared plus y squared equals 1. Now one thing, let's just review real quickly. If you have x squared plus y squared equals r squared, that's a circle of radius r, centered at the origin. A nice quick parametric representation for that is x equals r cosine t, y equals r sine t. Very nice parametric representation. And as you let t range from 0 to 2 pi, you go all the way around the circle. But the other thing to remember with representing your curve this way is t is an angle in standard position. T is given, so where is the point that corresponds to t equals 0? Well, the angle that's t equals 0 is right here. Where is the angle that corresponds to t equals pi over 2? In standard position, t equals pi over 2 is up here. and all the way around. This would be the point that would correspond to t equals pi, 3 pi over 2, and 2 pi. All right, so that's a nice thing to remember. Notice the x gets associated with cosine and the y gets associated with sine. So in this particular one, they want me to come up with the integral over c of 2 plus x squared y ds, where I have the lower half of the circle, x squared plus y squared equals 1. I can draw my circle. Okay, and we can notice my radius is 1 here, because square root of 1 is 1. So my parametric representation would be x equals 1 times cosine t, y equals 1 times sine t. But what does t need to range from? Well, they're talking about the lower half of the circle. So if this is t equals 0, this is t equals pi over 2, this is t equals pi, my t is going to range from pi to t equals 2 pi. Okay, now lastly, I have to figure out what's my ds. Okay, and I'm going to do that right here. My ds, remember, is the square root of dx dt squared plus dy dt squared times dt. Now notice, what's dx dt? Well, let's look here. If x is cosine t, dx dt is minus sine t. And if y is sine t, dy dt is cosine t. So if I want to figure out what's ds, ds is square root of dx dt is minus sine t squared, and dy dt was cosine t squared. Except, guys, what's sine squared plus cosine squared? 1, and square root of 1 is 1. So this one's quite nice that ds can be replaced with just dt. So now we have a parametric representation for x and y along this curve. We know what t is ranging from. It's ranging from pi to 2 pi. And we figured out what ds was. It's equal to dt. We're ready to do our substitution. Recalling, our integral that we're doing is 2 plus x squared y ds, s standing for arc length. So pulling this back, I say OK. First of all, what's t ranging from? From pi to 2 pi. Now I'm going to substitute for 2. Nothing gets substitute for 2. For x, I put in cosine t. For y, I put in sine t. And we figured out a few minutes ago that ds was just equal to dt, because sine squared plus cosine squared is 1. And now I have a simple integration to do. For this one, I'm going to do the integral of 2 dt as t goes from pi to 2 pi. And then I have to figure out what's the integral of cosine squared t sine t dt as t goes from pi to 2 pi. This one's very simple. It's just going to be 2t as t goes from pi to 2 pi. So if I pop in 2 pi, I get 4 pi. Pop in pi, I get minus 2 pi. And that subtracts out to 2 pi. Okay, now this one is going to take a little bit more work. So let's just put that one right here. We have cosine squared t sine t dt. What do you think our u substitution should be here? Cosine. U is going to be cosine t. So du is minus sine t dt. So since I have sine t dt, if I multiply through by a minus, I get minus du is sine t dt. So this integral becomes the integral of u squared, and sine t dt gets replaced with minus du, which is minus 1/3 u cubed, which is minus 1/3 u was cosine, so it's cosine cubed t as t goes from pi to 2 pi. And so if I plug in, I have minus 1/3 cosine of 2 pi cubed. Minus a minus is a plus, 1/3 cosine of pi cubed. And let's see, this one, cosine of 2 pi is 1. So 1 cubed is 1, that's minus 1/3. Cosine of pi is a negative 1. A negative 1 cubed is minus 1, so that's a minus 1/3. So that's minus 2/3 for that second integral. So coming back here, we just figured out this second integral is minus 2/3, and this one was 2 pi. So we're going to add 2 pi and minus 2/3, or our final answer is 2 pi minus 2/3. Okay? Simple U substitution, which at this point you should be all right already, Mrs. Strocko. I already know how to do that. Let's move on. Let's look at another example. Next one. In this particular one, they tell me they want us to integrate, they want us to figure out what is the integral over C of y over x ds. All right, that's right here. This is the integral that they want us to do. They're telling me that x is t to the 4th, y equals t cubed, and they're telling me t is ranging from 1/2 to 1. Now notice, when we do this integration, what do? We take our parametric representation. They're already telling me t is ranging from 1/2 to 1, so my integral is going from 1/2 to 1. Where I see y, I take it out and I put t cubed. Where I see x, I take it out and I put t to the 4th. Where I see ds, I have to do some work. Remember, ds is the square root of dx dt squared plus dy dt squared with dt on the outside. Notice, dx dt is 3t cubed. dy dt is 3t squared. So plugging that in, ds is square root of, parentheses, 3t cubed squared plus, oh, excuse me, that should be a 4. Thank you. This is a 4. Bring down your 4, yeah, 4t cubed. 4t cubed squared plus, this is 3t squared dt, which is going to give me square root of 16t to the 6th plus 9t to the 4th dt. Okay, and I'm going to put that in here for my ds. Okay, and now we have to deal with how do we do this integration. Well, first of all, I think most of you will agree, t cubed over t to the 4th is 1 over t. But notice in here, we could factor out t to the 4th. I'm using the fact that square root of a times square root of b is square root of a times b. So in here, I really just have 16t squared plus 9 dt. Right, because both of these are underneath the square root, this would give me this times this is 16 to the 6th, this times this is 9t to the 4th. And square root of t to the 4th is t squared. What was 16t squared plus 9 dt. And lo and behold, at this point, I can write this as 1/2 to 1 of 16t squared plus 9 to the 1/2 t dt. And how do I do that integration? A u substitution. I think I'm going to let my u be 16t squared plus 9. So my du is 32t dt, or 1 over 32 du is t dt. And therefore this integral becomes u to the 1/2, and t dt, I replace it with 1 over 32 du. Now notice, I do not put what my limits of integration are, even though some of you had told me, oh yeah, Mrs. Strocko, I can change them. Yes, you can, as long as you change them what u is when t ranges from 1/2 to 1. When I go through to do this, I end up with 1 over 32 times, increase my exponent by 1, divide by the exponent. So this gives me 2 goes into 32 16 times. 3 times 16 is 48. What is my u? My u was 16t squared plus 9 to the 3/2. And we're going from t equals 1/2 to t equals 1. I have 1 over 48, which I can factor out. If I plug a 1 in here, I have 1 times 16 is 16, plus 9 is 25 to the 3/2, minus, put in a 1/2, 1/2 squared is a quarter, quarter times 16 is 4, 4 and 9 is 13 to the 3/2. Now that answer is perfectly fine, except to get the answer like they have in the back of the book, please notice you can change 25 to the 3/2 you can write as 25 to the 1 plus a half. So it's 25 to the first times 25 to the 1/2, which is going to give you 25 times square root of 25. Square root of 25 is 5. 5 times 25 is 125. 13 to the 1½ is 13 to the first times 13 to the 1/2, which would be 13 times root 13. So what your book's going to do is they're going to replace 25 to the 3/2 with 125 and 13 to the 3/2 with 13 root 13. And that shows up enough times in our homework that I think it's something that you should be comfortable doing. Okay, let's look at this one. I like this one a lot because it gives me a circle. Will there be circles on your test? Absolutely. Everybody in here should be able to write a parametric representation of a circle. So this is a circle centered at the origin with radius 5. They want me to figure out the integral of xy squared ds, ds meaning arc length. And I say to myself, aha, I know what this circle looks like. Circle of radius 5. So my radius is 5. So Mrs. Strocko, x is 5 cosine t. Y is 5 sine t. Okay? But they're talking about the right half of the circle. Just the right half. So we have to find a continuum that we're going to let t range from, that I can start here and then I can end here. What is t here? Good, minus pi over 2. If you tell me 3 pi over 2, as I go increasing in this way, this becomes 2 pi, and then up here you better represent it as 5 pi over 2, which would be fine. You'll get the same answer. But I like letting my t range from minus pi over 2 to pi over 2. Okay, now before we do our substitutions, we've got to find out what ds is. So you should be getting real good at this. ds is equal to square root of dx dt squared plus dy dt squared times dt. And guess what? When we throw in a z there, you just throw in the dz dt squared. So my ds is square root of, well, if x is 5 cosine t, what's dx dt? Minus 5 sine t. And if y is 5 sine t, what's dy dt? 5 cosine t. So my ds here is square root of 25 sine squared t plus 25 cosine squared t dt, which I think we could factor out a 25 under the radical. And sine squared plus cosine squared is 1. So this is square root of 25, which is 5. So we have just evaluated ds can be replaced with 5 dt. It doesn't always get replaced with a nice simple number like this, but with circles a lot of times that's what happens. So now we're ready to do our integration. Our integral is the integral along the curve of xy squared ds. Okay. And so therefore, where I see x, what do I replace it with? I replace it with 5 cosine t. Where I see y, I replace it with 5 sine t. And where I see ds, I just figured out a few minutes ago, ds was 5 dt. And then lastly, what's t ranging from? T is ranging from minus pi over 2 to pi over 2. Now if you look here, what you have here is you have the integral of 5 cosine t times 25 sine squared t times 5 dt as t goes from minus pi over 2 to pi over 2. So let's see, I have constants 5 times 25 times 5, so that turns out to be 25 times 25, which is 625. Integral from minus pi over 2 to pi over 2, I think I'm going to write this as sine of t squared times cosine t dt. Everybody in here in Calculus 3 should be able to do that integration. What is it? How do we do it? What's our u? On the side, u is sine t, what you have in the parentheses. And so du is just cosine t dt. So this becomes 625 integral of u squared du, which is 625 625 times u cubed over 3, which will give us, now notice I've done the integration, so I have 625 over 3 times, what's my u? It's sine t, and we're evaluating it from minus pi over 2 to pi over 2. So this gives me 625 cubed. 625 over 3 times, pop in pi over 2, sine of pi over 2 is 1, 1 cubed is 1, minus, pop in a negative pi over 2, sine of minus pi over 2 is a negative 1, negative cubed is a negative 1. So this is 625 over 3 times 2, which we can write as 1250 over 3 as our final answer. Okay. Probably be a very good idea of you at home that after we set it up, you try setting it up before you watch the video and then fast forward to see if you got it right. And then you try to do the integration yourself and then fast forward it to see if you get the same answer as I did. Okay. We also, with line integrals, instead of integrating with respect to s standing for arc length, we can integrate with respect to x, with respect to y, and if we have a three-dimensional function with respect to z. Now the whole concept here is if you took a curve, here's your curve, and you partition it into a bunch of little subcurves. If I wanted to figure out the idea of f of xy dx, what you would do is you would break it up into a bunch of little subcurves. At each subcurve, take a point, evaluate your function at that point, and then multiply it not times the length of the curve, but how much x has changed going from this point to that point. Okay? And then sum them up, and then let your limit go to infinity, and that's what the whole idea of integration with respect to x. With respect to y, if you had a dy here, you would just be multiplying it times delta y. Now, hands-on, how would I go about doing it? Very simply. If you're integrating with respect to x, you get your parametric representation for c. X equals x of t, y equals y of t. Where you see x, you replace it with x of t. Where you see y, you replace it with y of t. And since x is a function of t, dx dt is equal to dx dt. Multiply through by dt on both sides. Dx is equal to dx dt times dt. So dx you replace with x prime of t times dt. And if you wanted to do it with respect to y, same thing. Replace x with x of t, y with y of t, and dy, taking this parametric representation, is just dy dt times dt. That's all there is to it. It's not hard. Not hard at all. So let's do one. The one I want to look at right now is this one. We want to figure out the integral of x e to the y dx. As we go along the curve 1, 0 to the point E1, they're just saying that this is the curve that's given x equals e to the y. They have not been nice. They haven't given me a parametric representation of the curve, and that's going to happen more and more often in this particular course. Notice, rectangularly, it's given by x equals e to the y. Now, do you notice I look at that and I say to myself, if I let y be t, it's very easy for me to let x be e to the t. Do you all see that? I have a beautiful parametric representation for my curve. Do you see that? I have x, since x equals e to the y, and if I let y be t, x is given by e to the t. Now notice, my point, I'm going from 1, 0 to E1. Now notice, in my parametric representation, y is t. So here is your y here. And since y is t, we have t ranging from 0 to t ranging from 1. Does everybody see that? Because my point is 1, 0 to E1, but since I let y be t, t is ranging from y is 0 here to y is 1 there. Okay? And notice this works because if y is t, x is e to the y, I replaced y with t. Okay, now to do my integration is very, very simple. Let me just put the integral right here. We're doing the integral of c x e to the y dx. Okay, I'll just put it right there. So what do? I look at my parametric representation. I have t ranging from 0 to 1. What's x? X is e to the t. This is times e to the y, but since y is t, it's e to the t. In addition, I'll put this in green. Since x is e to the t, dx, remember, is dx dt times dt. If x is e to the t, the derivative of x is e to the t. So I replace dx with e to the t dt, because we're using the fact that dx is dx dt times dt. X is e to the t, so I have e to the t dt. So dx is getting replaced with e to the t dt, which looks quite weird. I have e to the t times e to the t times e to the t dt. So how am I going to do that integration? It's going to be the integral from 0 to 1 of e to the 3t dt. How do I do that integration? What do we let u equal? Remember, we know the integral of e to the u du is e to the u. So what's my u? U is 3t. So du is 3 dt, or 1/3 du is dt. So if I make my substitution here, e to the 3t becomes e to the u, but dt gets replaced with 1/3 du. So I really have 1/3 integral of e to the u du. E to the u du is e to the u. So it's 1/3 e to the u, which is 1/3 e to the u was 3t. And we're going from t equals 0 to t equals 1. So I like to factor out my constant here. Popping in a 1 gives me e to the 3rd minus putting in a 0, e to the 0 is 1. And that's my final answer. Okay? So if you ask me, the hardest part's the integrations. Let's do another one. Oh, no. Quite often, frequently, when we have something like this, we are asked to come up with the parametric representation for a line segment going from one point to another point. Just to remind you of how you get your line segment, remember, if you had a point right here, and we can make like the x, y axis go like here, and there's another point on the line, x1, y1. Vectorially, we need the vector r0 pointing me to my initial spot, and then I need to have the vector showing me in what direction I go. I'll call that r1. And remember, if you take r0 and then you stretch r1 with different ways, you get that whole line here. So our equation of our line is going to be our position vector that gives me a point plus t times some vector r1, which is the difference of those two. Remember doing that? Or another way, if you're having a little trouble remembering that, you might remember in 3-dimensional space or in 2-dimensional, your parametric representations were x equals x0 plus at, y equals y0 plus bt, z equals z0 plus ct. What was your x0, y0, z0s? What were they? They were a point on the line, right? What was ABC? That was a vector in the direction of the line, right? Okay, well here, if I want to come up with a parametric representation for the line segment that goes from x0, y0 to x1, y1, think, here's x0, y0, here's x1, y1. If I want to get a vector that's going in the direction of this line, because my line is here, can anybody give me a vector that's in the direction of that line? It would be x1 minus x0, comma y1 minus y0, wouldn't it? Sure, you just subtract them, right? That vector, the vector going from here to here, has these for its components. So if I call this vector A, the A component, and this the B component, the parametric representation for this line would be x equals x0 plus at, y equals y0 plus bt, where x0, y0's a particular point on the line, and t and And A and B are the components you get of the vector by subtracting this point from that point. And that gave you that vector right here. In particular, let's do one in particular. Suppose I want to get the parametric representation for the vector that goes from the point 2, 3 to the point 5, 8. What's your x naught, y naught? You could use 2, 3 or 5, 8. I'm going to use 2, 3. What is your vector AB that goes from this vector to that vector, from this point to that point? It's going to be 5 minus 2, which is 3, and 8 minus 3, which is 5. That's your AB. So your parametric representation is going to be x equals 2 plus 3t, x naught plus at, and y equals 3 plus 5t. Now let me ask you something else. If I want to go from this point to that point, what do I let t range from? Well, notice if you let t be 0, you're right at that point, aren't you? If you let t be 0, your x is 2, your y is 3, you're right at that point. What do you have to let t be to be at the end point? Let t be 1. Let t be 1, you're going 2 plus 3 is 5. 3 plus 5 times 1 is 8. Well, sure, because what are you doing? Here you had your point 2, 3, and you figured out what's the vector from 2, 3 to 5, 8. Well, if you add that whole vector, you're going to be right there at 5, 8. So if you let t range just from 0 to 1 with this parametric representation, you're going to be going from this point to that point and no further. Notice if you want to do it in 3D, if we wanted to go from x naught, y naught, z naught to some point x1, y1, z1, let me do it with specifics instead of arbitrary letters. What if I want to go from 1, 2, 3 to 4, 8, 7? This is your x naught, y naught, z naught. Okay? Give me a vector, A, B, C, that goes from here to here. What do? Subtract your x's, y's, and z coordinates. So you're going to go 4 minus 1 is 3, 8 minus 2 is 6, 7 minus 3 is 4. So what's my parametric representation going to be? X equals x naught plus at, y equals y naught plus bt, z equals z naught plus ct. So in this particular case, it would be x equals initial points 1 plus 3 times t, y equals 2 plus 6 times t, and z equals 3 plus 4 times t. And what does t range from? 0 to 1. Check yourself before you go on and do all the mathematics that you have to do. Notice, if you plug in 0 in here, what's your point? 1, 2, 3? Yeah, it's my starting point. If I let t be 1, am I at my end point? Sure. 1 plus 3 is 4, 2 plus 6 is 8, 3 plus 4 is 7. I have the parametric representation of the line segment that goes from 1, 2, 3 to 4, 8, 7. Well, let's do this. What I'm doing now is I'm going to be doing the integral of x ds. I'm doing it over two different curves that connect the point 0, 0 to 1, 1. Here's the point 0, 0, and let's say here's the point 1, 1. This first curve that I'm doing this line integral from is the straight line that goes from the point 0, 0 to the point 1, 1. We want to figure out this integral along the line segment from 0, 0 to 1, 1. In a few minutes, we're going to do it along the curve y equals x squared. And you all know what y equals x squared. It looks like that, coming this way. And my point is this. If I took this path and if I take that path, we should get two different answers. So the point is we want to make the point that in general, the value of a line integral depends on both the path and the endpoints, not just the endpoints. Okay, this one, we have to get a parametric representation for this curve that goes from 0, 0 to the point 1, 1. I want to use x equals x naught plus at, y equals y naught plus bt. What is my vector that goes from this point to that point? Well, my vector AB is quite simply 1 minus 0, which is 1, comma 1 minus 0, which is 1. So my parametric representation is going to be x equals my first point, which is 0, plus 1 times t, and the other one's going to be y equals 0, plus 1 times t. So we're going to let x be t and y be t. And t is ranging from 0 to 1 as we go from this point to that point. Now we've got to figure out what is our ds. Remember, ds is square root of dx dt squared plus dy dt squared dt. So it's going to be the square root of, now if x is t, dx dt is 1. If y is t, dy dt is 1. And so it looks like we have square root of 1 plus 1, which is square root of 2 dt. Okay, now doing our integration here, they want us to figure out, in fact, why don't I just copy it over here, the integral of x ds. All right, and x is t. And ds is square root of 2 dt. And we have t ranging from 0 to 1. So quite simply, this is square root of 2 integral of t dt from 0 to 1, which is square root of 2 times t squared over 2 from 0 to 1, which gives us square root of 2 times 1/2 minus 0. So we have square root of 2 over 2 for our integral. Okay, so what have we done so far? If we take the curve, the straight line from 0, 0 to 1, 1, and go that way, the integral along that curve of x ds, we got to be root 2 over 2. All right, now we want to do the exact same thing again, but this time I want to go along the curve y equals x squared. And I have to come up with a parametric representation. Well, you guys tell me, can you come up with a parametric representation? What do you want to let, one way to do a parametric representation is to try to let one of the variables be t. Well, since y is written in terms of x, doesn't it make sense? Why don't we try letting x be t? And if x is t, what's y? T squared. And since we're going from 0, 0 to 1, 1, in this particular case, t is ranging from, when we're at 0, 0, since x is t, or t is x, and x is 0, t is 0, to, when we're here, t is 1. There's our lovely parametric representation. Now we want to find out the integral along this curve of x ds. The only thing left for us to do is figure out what's ds, right? So we have a little bit of work to do. To get ds, what do we have to do? ds is square root of dx dt squared plus dy dt squared dt. So ds is square root of, now since x is t, dx dt is 1. Since y is t squared, dy dt is 2t. So it looks like ds is square root of 1 plus 4t squared dt. Okay? So plugging this in now, we are figuring out the integral of x ds along this curve. Our parametric representation had x was t, so where I see x, I replace it with t. ds is 1 plus 4t squared dt, and we had t ranging from 0 to 1. This is a simple u substitution, isn't it? It's not all that tough, is it? What are we going to let u be? What are we letting u be? U is going to be 1 plus 4t squared. So du is 8t dt. Since I have t dt, maybe you want to multiply through by an eighth on both sides. So 1/8 du is t dt. So this integral becomes the integral of, this is u to the 1/2. T dt I replace with 1/8 du, which gives me 1/8 times, increase my exponent by 1, divide by the exponent. Let's see, 2 goes into 8 4 times. So I have 1/12 times u. U is 1 plus 4t squared to the 3/2 as t goes from 0 to 1. This is equal to 1/12 times, if you pop a 1 in here, you have 5 to the 3/2. Pop in a 0, 1 to any power is 1. And you can't help but say 5 to the 3 halves is 5 root 5, like we did a few minutes ago, writing as 5 to the 1 times 5 to the 1 half. Notice the integral along C2 of x ds was 1/12 5 root 5 minus 1. Along the straight line, we got root 2 over 2. Along the parabola, we got something entirely different. So line integrals in general depend very, very much on the path and the endpoints that you choose. Okay, a few more things I want to tie up. I did everything so far in two-dimensional space, but three-dimensional is no different at all. I could have a curve in space. X is given as x of t, y is given as y of t, z is given as z of t. Same idea. ds, if you're in 3 dimensions, is going to be dx dt squared plus dy dt squared plus dz dt squared. And the integral along your curve of f of x, y ds is you're going to plug in for x, y, and z in terms of t here for your function f. And your ds just has that dz dt squared component. No different. Okay? So, what if I want to find out the integral along the curve of x squared z ds? All right? First of all, what the hardest part is, if you ask me, is you have to get a parametric representation of the line segment from the point 0, 6, negative 1 to the point 4, 1, 5. Okay? We have to get a parametric representation for that line segment. This is my x naught, y naught, z naught. Direction matters. My line segment's going from this point to that point. Okay? Now, what's my vector A, B, C that points me from this point to that point? What do? We take final minus initial, don't we? So this vector is going to be 4 minus 0, 1 minus 6, and 5 minus a negative 1. Or my vector ABC is going to have components 4, minus 5, 6. In general, my parametric representation for this line segment is x equals x naught plus at, y equals y naught plus bt, z equals z naught plus ct. Okay, and plugging that in, what do we get here? We're going to have x equals, my first point is 0, my a is 4t. Y equals, my initial y coordinate is 6 minus 5t. And my z is going to be a negative 1 plus 6t. Before I do anything else, I make sure that this parametric representation works. Notice, t always ranges from 0 to 1 when we do it this way. If you plug a 0 in here, you get the point, 0, 6, negative 1. If you plug in a 1, you better be back at 4, 1, 5. And plugging in 1, 0 plus 4 is 4, 6 minus 5 is 1, negative 1 plus 6 is 5. Yes, I did it. Okay, lastly, before we do anything else, we got to find out what's ds. Well, notice if x is 4t, dx dt is 4, dy dt is, if y is 6 minus 5t, dy dt is negative 5, and dz dt is, derivative of that is 6. So my ds is square root of dx dt squared plus dy dt squared plus dz dt squared times dt, which is going to give me square root of dx dt is 4, 4 squared is 16, dy dt is negative 5, square that you get 25, dz dt is 6, square that you get 36. So this turns out to be a square root of 77 dt. Okay, now I'm ready to do my substitutions. Okay, so what was the integral that we're doing? Pulling this back. The integral that we're doing right here is we're integrating along the curve of x squared z ds. All right, now coming back here, what did we have x to be? We have x is 4t. Z is minus 1 plus 6t. And ds a few minutes ago I figured out was square root of 77 dt. And t for this line segment was ranging from 0 to 1. I'm not going to go do this. This is a you multiply it out. You integrate it term by term, and when you're done, you're going to get 56/3 root 77. I'll do the ones that I think you need review on, but this is a simple polynomial. Just multiply it out and then integrate it term by term. And definitely drop kick that square root of 77 to the front as a constant. Okay, we doing all right? Okay. Let's look at this one. Oh, we just did this one, thank goodness. In this one, I have a curve that consists of two line segments. My first C1 goes from 2, 0, 0 to 3, 4, 5. And then I go from 3, 4, 5 to 3, 4, 0. What we're doing here with this one is we're going to use the fact that if your curve is the union of two curves, then your integral over that total curve is the integral over C1 plus the integral over C2. Okay? All right, now we're going to go through and do this one. Notice C1 goes from 2, 0, 0 to 3, 4, 5. Those of you that are home, stop the tape right now and see if you can come up with the parametric representation for this line segment from here to here. Those of you in the audience just have to bear with me, okay? This is my initial point, x naught, y naught, z naught. What's my vector? A, B, C, that goes from this vector to that vector. You subtract. You're going to go 3 minus 2 is 1, 4 minus 0 is 4, and 5 minus 0 is 5. So my parametric representation will be x equals x naught, which is 2, plus a times t, which is 1 times t. Y is going to be 0 plus b times t, 4 times t. And z is going to be 0 plus 5 times t. So my parametric representation is going to be x equals 2 plus t, y equals 4t, and z equals 5t. And what is t ranging from? 0 to 1. Plug in 0, you do get the point 2, 0, 0. Plug in 1, you get the point 3, 4, 5. The next thing that we have to do is just find out what ds is. Notice ds is square root of dx dt squared plus dy dt squared plus dz dt squared dt. So it's the square root of, let's see, dx dt is just 1, so it's 1 squared. Plus dy dt is 4, square it gives me 16. dz dt is 5, square it gives me, let me look at what the, oh, excuse me. I'm looking back at the integral. This integral is not of some function ds. Notice it's the integral of y dx plus z dy plus x dz. It's not with respect to ds, so I apologize. Get rid of that. We're going with respect to x, y, and z. So back here, let's look at our parametric representation. This is even easier. Our parametric representation for this line segment C1 has x equal to 2 plus t, y equal to 4t, and z equal to 5t. Let's find out, what is dx? Well, remember, dx is dx dt times dt. Well, if x is 2t, dx dt is 1, so it's 1 times dt. dy is dy dt, which is 4 times dt. And dz is dz dt, which is 5 times dt. And notice our t is ranging from 0 to 1. Now, the integral, I'm just going to copy it right here, is the integral of y dx plus z dy plus x dz. Plugging that in, look what you get here. Y is 4t. dx is dt. Z, what's z? Z is 5t. dy is 4 dt. Plus x. X is 2 plus t. 2 plus t. dz is 5 dt. And we're going from t equal from 0 to 1. So notice if you multiply this out, you get 4t plus 20t plus 10 plus 5t, and I could factor out the dt and put it at the end. Well, shoot, guys, this is the integral from 0 to 1 of 29t plus 10 dt. I don't think you need me to go do that integration. You guys can go and do it, and you're going to get 24.5. Okay, so this is the integral over C1 of blah, blah, blah was 24.5. Now, right now we sit and we think, oh, she's got to do C2, but I really need to do C2 for a reason, and let me show you why. C2 is a very nice one. When you get a C2 like this on your test, you say, Mrs. Strocko, I like you. Notice C2 goes from 3, 4, 5 to 3, 4, 0. Notice your vector A, B, C, which you get by subtracting. It's 3 minus 3, which is 0, 4 minus 4, which is 0, 0 minus 5, which is a negative 5. So we have x equals x naught, which is 3, plus 0 times t. Y is, see, it goes 0 times t, which is 3. Y is y naught plus 0 times t, which is 4. And z is z naught plus negative 5 times t. Now notice this, people. If x is 3, what's dx? Well, it's dx dt times dt, but what's dx dt? 0. dy is 0. dz is a negative 5 dt. So when I go back to this integral y dx plus z dy plus x dz, and I'm going to go evaluate him, x is 0. dx is 0. dy is 0. So this integral becomes the integral of x, which was 3, times dz, which is a negative 5 dt, as t went from 0 to 1, which gives me a negative 5 integral of dt, which gives me a negative 15t, and we're going from 0 to 1, so we get a negative 15. So my integral along C2 of blah, blah, blah turned out to be a negative 15. And since C was the union of C1 and C2, the integral along C is the integral of C1, which was 24.5, plus the integral of C2, which is a negative 15, and I think that adds up to a positive 9.5. Okay? All right, we have a couple more little things I just want to touch. Notice, in many respects, we see this notation f dot dr. We're going to be doing a lot with this later. You could write, if you wanted to know the integral of some vector-valued function f dot dr, you could write it as f of r of t dot r prime of t dt. You could rewrite this piece right here by dividing by the magnitude of r prime and multiplying by the magnitude of r prime. This piece right here, you might remember, was your unit tangent vector, t. And this piece right here, if you play with it, you'll see that it's ds. We'll be bringing this up again. You don't really have to know how to do it for the homework. It's not going to show up. But just, you might want to save this and use it for reference later. One last thing. If I have a function written as f equal to some component p, I, q times j plus r times k, I want you always to think of the vector dr as being dx times I plus dy times j plus dz times k. All right, your little pieces of how much x, y, and z. The integral over the curve of f dot dr, remember, dot product is multiply your x components plus your y components plus your z components and add them up. So when you see this f dot dr, it means this. As our last example, let's do this one quite quickly. We have f of xy is equal to the vector x minus z plus y. So f has components x minus z and y. Vector r is given by, notice vector r is given by 2t, comma, 3t, comma, minus t squared. Now if we want to get dr, what we do is we differentiate each of these with respect to t and then multiply by t. Just like dx was dx dt dt. So this is going to be, the derivative of this is 2, derivative of that is 3, minus 2t, and then we have to multiply by dt, because it's dx dt times dt plus dy dt times dt plus dz dt times dt. So that we have dx, dy, dz. Now notice, if you take f dot dr, the dot product of this with this, look what you get. 2 times x plus 3 times minus z plus negative 2t times y dt. Okay, and they want us to figure out the integral of f dot dr. Now bringing this back, notice t is ranging from -1 to 1. This is my curve. On my curve, notice x is 2t, y is 3t, and z is minus t squared. So, looking at what I had with f dot dr, I have the integral of 2x minus 3z minus 2ty dt as t goes from -1 to 1. But on the curve, x is 2t. So we'll have the integral from -1 to 1 of 2 times 2t minus 3 times z, which is minus t squared, minus 2t times y, which is 3t, dt. And it's a simple polynomial that you have to do, which if you do it, you will get a -2. Okay, now what I want you people to do is I want you to read pages 1098 to 1107, and then on pages 1107 to 1108, 1 through 15, the odds, 19, 21, and 25. Okay, I'll see you next time.